Hey now, how's everybody doing? Hope we're all getting through this first week of distance learning. Today's lesson, we're going to kind of continue where we left off the other day. So last class we discussed porosity. So let's see what you remember. So here I have a tube with big sediment, pebbles, tube A. Tube B is medium-sized sediment, sand. And tube C has smaller sized sediment called silt. Before I go any further, in one of your pages in your reference table that I'll go over another day, they actually discuss each of the different size sediments, so you don't have to memorize them. But you probably know all their names again. For example, the biggest sediment is a boulder. What's bigger than a boulder? Nothing. Because a boulder is the biggest size sediment that's not rooted to the earth. All right? So if I break a boulder, I get these things that a lot of us might see in old city streets. They're called cobbles. So boulders are the biggest, then cobbles. And what if I get if I break a cobble? That's right, 4 perfect pebbles. All right? And what do I get if I break a pebble? Sand. And how about if I ground down sand? Then you get silt. Some of us might call silt sand as well, because you really can't tell the difference unless you have like a really good strainer with all the different dimensional holes. And what's smaller than silt? Clay. So clay is your smallest material for sediment. It's also a group of minerals, but for this unit, we're going to use it as a sediment size, not as a mineral. Most people don't realize how small clay is because it looks like one big piece when you use modeling clay, but it's actually thousands of little pieces stuck together. So back to this little model here. So I have big sediments, pebble, medium sediment, sand, and a tube with small sediment, silt. I already filled them all with water, so the white circles are the sediment, and blue, it might look black in your screen, is the water that has filled the pore spaces. So last class, what we go over, which one should be able to contain more water? And the answer was they should be equal. All right? They have equal porosity. So let's say all 3 of them, just to keep it simple numbers, had 100 milliliters in them. 100 milliliters in this, 100 milliliters in that one, and 100 in the smallest one. Okay? And then in the bottom of the tubes, there was a hose. And at first I clamped it, so water couldn't come out. Now every year we usually do a lab on this. And I would set up three long, they're called settling tubes. And we would fill them with big marbles, medium marbles, and small marbles. And we will actually calculate the porosity, and then we would let them drain. All right? So the homework that you had the other day, a lot of you didn't get the answer correct, but hopefully you read my message. If you did the math properly, you should have got 13.76 for both answers. The porosity should have been identical. All right? So let's say they're all filled with water. I have a hose at the end of it, and I allow them to drain. So water is going to drain out of all 3. So let's say I did a race, and I was able to let 3 of the hoses go all at the same time. Which one do you think would win the race? The biggest, the medium, the smallest? Or do you think it would be a tie like porosity? Well, the answer, the biggest will win the race. All right? And the reason is it will be easier for the water to travel or navigate from pore to pore. So the pores in here, because they're bigger, are easier to travel through. Or you could say they're more or well connected. So the water would have an easier time getting from the top down to the bottom. This one would have to make more turns, but eventually it would escape. While this one, it would take an extremely long time to get out. All right? So the way we could phrase this is in 2 different ways. We would say this one has the greatest permeability, and this one has the lowest permeability. Another way you're going to see this on the reagents and on one of my tests is we would say this one has the greatest infiltration rate. So whatever has the greatest permeability will allow water to infiltrate through it the fastest. And this would have the slowest infiltration rate. All right? So let's say this one drained in 2 seconds. This one would drain maybe in 5 seconds. And this one, they're so small, that might take like a whole minute. All right? The smaller sediment, clay, takes such a long time to drain that it's considered impermeable. So water has a hard time going through it. So let's define permeability. Permeability. So it has the word ability in it. So it's the ability for water to permeate or travel through a material. Sorry. Ability for water to travel through rock or sediment. Man, my handwriting is horrible. All right? Another way we would describe it is how well the pores are connected. So it describes how well pore spaces are connected. All right? So the bigger the pores, the easier it is for water to get from one to the next. That means they're well connected. While here, the pores are so tiny, they're not as well connected. So this has a high permeability, low permeability. So water will infiltrate quickly through this one. So high infiltration rate, and very slowly through this one. All right? So there was a question in the textbook reading tonight, or today, whenever you chose to do it. And the question was, can a rock have a high porosity, yet a low permeability? And the answer is yes. And that would happen if the pores weren't well connected. I like to think of like a house of cards. So ever see someone make a house of cards with like playing cards? So you would have a card standing up, and then a card balanced, and then another card standing up, another card balanced, and you would make your house of cards. So in that house of cards, are there a lot of rooms? Sure. So each of those rooms is a pore space. But imagine you were in room here, like you were X, and you were in this room. It would be nearly impossible for you to escape this room and get to the next room. So even though this represents something with a good deal of pore spaces, right? These would all be pore spaces. None of those pore spaces are connected. So this could be something that's like 90% pore space. So we would say 90% porosity, yet actually it's impermeable. And there are things in nature that are very similar to this. Pumice, which we'll learn about, which is a volcanic rock. Vermiculite, which is used a lot to stop water from entering the ground. So like if you wanted to, you would use vermiculite to maybe coat the bottom of a pool. So it's very porous, but it's not permeable. And clays. All clays are extremely porous, so they will absorb water like a sponge, but they don't let the water out. And that last example I just said, a sponge. A sponge is all pores, but a sponge is really impermeable. Because the only way to get the water out of the pores is to squeeze it. The water doesn't just flow through it. All right? So it is possible for a rock to have a high porosity and a low permeability. Okay? All right. The next concept I want to go over is retention. So we did our permeability race. This one won. So let's say this one took 2 seconds, 5 seconds, a minute. And remember, we put 100 in. So let's say after I drained it, do you think I would get exactly 100 out? And the answer is no. Maybe I'll only get 98 out. So where's the other 2? Well, the other 2 is stuck to the surfaces of the pebbles. Okay? So we would say 98 infiltrated and 2 milliliters got retained. All right, now you look at this one. Well, these are smaller now. So if it's smaller sediment, is there more or less surfaces? And there's a lot more. So that means there's a lot more surfaces for the water to stick to. So this one, I got 98 out of. Maybe I'll only get 90 out of this one. Which means this one retained 10. Because remember, we started with 100. So 90 infiltrated through, and 10 got stuck in. That's what means it got retained. All right? Well, this is the smallest sediment. So there's the most surface area. Well, the most surfaces to stick to. So, do you think I'm going to get more or less than 90? Well, if we look at the pattern we've been looking at, it should definitely be less than 90. So maybe we'll only get 80 out of here. 80. So how much did it retain? Well, we put in 100, got 80 out, so it retained 20. All right? So the smaller the particles, the higher the retention. So right now I want to just draw 2 graphing relationships. And of course you could copy them in your notes. The first one would be permeability. Size versus permeability. So how does size affect permeability? And for porosity, remember it was a flat line. But for this one, the larger the pores, the easier it is to travel through. So it's a direct relationship. Okay? And the other one I want to draw is how does size versus retention. Once again, I put my size here. This is how does size affect retention. And if you remember the picture a second ago, the smaller it is, the more it retained. And the bigger it was, the less we got out. So that means the less it retained. So the bigger it is, the lower the retention. Okay? So I hope you got a lot out of yesterday's video and today's. I want you to leave with thinking of one thing. Okay? So in order to be a great learner, number 1, your brain must be porous. Number 2, it has to be permeable. And that's probably most important. So true geniuses, the information can travel through the brain from one area to the next. But in order to do well on the test, your brain has to retain that information. All right? Have a great night.